Welcome everyone to our second virtual astronomy lecture that we're hosting online on YouTube Live. I'm Dr. Cameron Hummels, a postdoctoral researcher in the astrophysics department at the California Institute of Technology, and I will be the MC for this evening. We've got a great program tonight. We've got an excellent talk by one of the up and coming researchers in our department who's finishing his PhD in the next year. And then we've got a Q&A panel at the end. So essentially the layout for tonight will be a 30-minute talk given by Yuguang Chen on the gas around galaxies. And then following that, we'll have a 90-minute Q&A panel consisting of members of the department who work on a variety of different topics, answering your questions, either that you put in the YouTube screen, the YouTube question log on the side, or that you've submitted over social media, Twitter, Facebook, Instagram in advance. So we have a number of questions that have already come up. While we're just getting started, to make sure we don't have any people showing up late or lagging, I wanted to do a really quick demo of something that I think is really cool, because normally at our events we have a stargazing component, but obviously we can't really do that online right now. So, and it's still sunny outside, so you can't see the heavens from here in Los Angeles. But there's a really cool piece of software that I really like. It's open source. It's free. You can download it for Windows, for Mac, for even Linux. And it gives you a visualization of what the sky looks like overhead and the different constellations, the different stars, the different planets that are visible from any arbitrary location and at any arbitrary time. So I will share my screen. It's called Stellarium. And this is what the sky looks like overhead right now. As you can see, there's still some sunlight, so we can't really see anything, but I'm going to move ahead, and so an hour in advance. So at 8 o'clock tonight, this is what we will see when we look up overhead. In the direction at the bottom of the screen is south, at the top of the screen is north, and you can make out a few things, like here you can see the Big Dipper is visible in the northern part of the sky, or Orion is visible. But what's really cool about this is you can zoom in and see imagery of what certain things look like. So I'm going to zoom in on what's called the Orion Nebula, which is in the center of the sword hanging off the belt of Orion. And when we zoom in, we can see an image of what the Orion Nebula looks like, this stellar nursery that's surrounded by gas and dust and really young, massive, hot stars that are ionizing all of the gas around them. And it creates this really beautiful image. Now, this is what you would see if you looked at it with a really high quality telescope, usually larger than most consumer grade telescopes, and from a dark sky site, out in the middle of the desert or in the country. But there are a number of different cool things that we could see tonight if we had our telescopes out. Over here, we can see the Pleiades star cluster. This is also known as the Seven Sisters. So it actually always looks to me like there are six bright stars, but there are many members of this cluster. Venus is up and visible, and if we zoom in, we can see that Venus has phases, just like the moon has phases when it's partially illuminated, when it's illuminated from the side. I'll zoom back out. And we can see that over the course of the night, if we kind of tromp forward through the night, now it's midnight, 1 a.m. Oh, the moon's up. And then later in the morning, here we can see the band of the Milky Way across the sky, and we can see Jupiter, Saturn, and Mars that are all visible just before sunrise. So if you're really ambitious and want to wake up early in the morning, you'll get a glimpse of 3 of the coolest planets out there. We can zoom in on Saturn and see. It's awesome. Well, sometimes it crashes your computer. or at least crashes the program. Fortunately, it doesn't seem to have crashed the entirety of my computer. But that was about all I wanted to show with Stellarium. It's a great program, so it's something that's fun to play around with during the quarantine, and it's totally free. Anyway, we'll get on with the rest of our show. So our speaker for tonight, as I mentioned, is Yuguang Chen. He's a PhD candidate. His specialty is on the circumgalactic medium and the evolution of galaxies. And to study these, he uses the largest telescopes on the planet in the optical and in the infrared. And I will, let's see. Sorry about that. We'll get on with the rest of our show. Oh, shoot. So our speaker for tonight, as I... Here we go. All right. Yuguang, are you there?
Yes.
Sorry about this. All right, I will let you take it away, Yuguang. Thank you.
Cool, perfect. Thanks, Cameron, for the introduction. And also thanks for, even though it's crashed, the Stellarium show. So today, I'm gonna talk about the gas around galaxies. So let's start with a common interpretation or common conception of what a galaxy should look like. So this may be one of the things that come into your mind. And if you know somewhat a little bit more about astronomy, you may think about, okay, this is not a full picture and the galaxies on the right, maybe if we consider all of them, maybe the full picture of a galaxy. And today I'm gonna tell you that all of these are wrong. These are not full pictures, even though they are part of the galaxy, but they are not the full galaxies themselves. So I want to start my talk with a mystery. So when talking about mysteries, sometimes we start with this, a long, long time ago. And indeed, this is a long time ago. So I want to start my talk with mid-20th century. And the mid-20th century, we see a booming astronomy research on galaxies that are outside of our own Milky Way. And many of these researches are actually fueled by our neighbors, by the astronomers in Pasadena, especially by astronomers in Caltech, and also the Carnegie observatories that just cross the highway, 210 freeway. And the reason is that in the early 20th century, in 1920s, we know that Edwin Hubble discovered that there's, beside of our own Milky Way galaxy, there are a lot of more galaxies outside of it. So we suddenly realized there are so many things that we can study. And in one of these discoveries is something that you probably heard of. It's called the quasi-stellar objects, or in short, quasars. So these things look like stars. These things look like just in optical, they look like just a infinitely small source. So it looks like perfectly like a star. But it's discovered in radio telescopes. So in those giant radio dishes, so you point these radio telescopes at some area of the sky, you see very strong radio emission. So they discovered in radio. One thing that you can do when you find the optical counterparts is that you can put them in a spectrograph. And let me quickly remind you what a spectral graph really is. So imagine here is that light, is that quasar, is that stellar-like source. You somehow find a way to divert the light into a prism or some other optical elements that can disperse the light. It disperses the light into a rainbow. And so here, this is the purple end of the spectrum. So it's the small wavelength part. And here is the red part. So it's the long wavelength. And here is a typical looking of what the spectrum of a quasar really look like. And you can immediately see some very strange features. I bet you already can tell that there's a clear boundary splitting the blue and red sides of this spectrum. There are more absorption lines on the blue side and less absorption lines on the red side. So what causes this? To understand that, oh, by the way, I'm going to jump straight in and claim that even though this cost a lot of astronomers a lot of time back in the day, but I'm going to jump in and claim this spectral feature here is caused by hydrogen. It has a name called Lyman alpha. It's being emitted at 121 nanometers and for this certain quasar, it's being observed at 562 nanometers. So to understand what causes this, let's start with the expansion of the universe. So we know that the universe is expanding and it looks like a balloon. It's being shown here as a balloon. So at the time, so we all live in this universe, and in this universe, there are certain things like electromagnetic waves or photons. So for these electromagnetic waves, they have a very special characteristics. They expand as the universe expands. So for example, here is an electromagnetic wave in the balloon in an older universe, in the universe that's in the past. So the universe is smaller. And then in the current universe that we are in, because the expansion of the universe, these electromagnetic waves also expand, also get stretched. So we get longer wavelengths. So that's why when we observe a certain spectral feature, we see them in longer wavelengths, and when they are being emitted in the past universe, they are in shorter wavelengths. So trust me, this is the first of the two equations that I'm going to show tonight. So don't be panicking. This is very easy. So we define that the wavelength of the absorbed over the wavelength that's being emitted equals to the ratio, and that ratio is 1 plus z. For some reason, there's 1. And the z is what we call redshift. So a larger redshift means that there's a larger ratio between these two, between the observed wavelength and the emitted wavelength. That also means the emitted wavelength is smaller, right? Because we have a ratio that's being larger, so lambda emission that's smaller. This also means, because this ratio is larger, and also because this wavelength is smaller, that also means at the time of the emission, the universe is much smaller. So it means it's a younger universe. Also means it's more distant. When this light is being emitted, this object to us is very distant because the light travel needs some time. For example, when z equals 2, that means redshift equals 2, it's just a number. It means that at the time of the emission, the source is from us, the source is 10 billion years ago. And it also is 5 billion light years away from us. So very distant and very ancient source. Now, what happens to those spectral lines? So imagine you have a source here, and it passes along through the universe gradually, because the light travel costs time, gradually it passes through the universe. And then while it passes through the universe expands. So this wavelength gets stretched, can be moved to the right. And then at a certain time, there's something that can absorb at this wavelength. So for example, if you have something that absorbs here, it will leave an absorption at 120 nanometers at that time. So it will be here and then gradually shifted to the right. So that's why we see this called Lyman alpha forest, because it looks like a forest even though it's the other way around. So let's go back to this spectrum. In fact, I cheated here. This is a fairly recent spectrum of a fairly distant quasar. I cheated here that I didn't show you what originally people found in 1960s. This is what they saw. And you can immediately tell first, the spectrum looks really crappy compared to the other ones. That's for sure, because it's almost 60 years ago from now. And also, you can see the features are less. That's due to two factors. One is because this quasar is very close to us. And also because because the spectral resolutions and also the spectral qualities at the time, because the telescoping instruments are crappier than what we can get for now. But even with this sort of quality of the spectrum, astronomers, particularly 3 astronomers, all associated with Caltech at the time, identified 49 lines from here. They grouped them by redshift because you can have multiple different absorption lines caused by the same system at different redshifts. And also, they group them by elements. And how they do this, before that, I really want to say something. When you take a picture, don't be in front of, have some variety. Don't be all in front of bookshelves, for example, here. So these are all, so these 3 astronomers group them, and how they do that? So first, you see in the spectrum, there are some doublets. For example, here, these 2 doublets, it's caused by the element called carbon, and we are all very familiar with them. And if you find more other doublets, you may saw here, oh, here it's another doublet. So these 2 are in fact all caused by the carbon element that's absorbing this, that creates this doublet feature and also cause the absorption. But they are at different wavelengths. That means they are at different redshift. So now, if you think, okay, that's partly convincing, but there are a lot of other things can cause doublets. So they can also go back and check, because they know the redshift now, they can go back and check, is there any other elements that can cause absorption at the same redshift? Turns out there are. So these 2 absorption lines are here and here are caused by silicons, and at this exact same redshifts as these 2. So you think, okay, now is there a Lyman alpha absorption? The answer is yes, but unfortunately, this spectrum has a very limited spectral range. So Lyman alpha would be, the Lyman alpha absorption here would be all the way to the left. So unfortunately, we can't see that. But fortunately, we have some we have Lyman alpha absorption and other redshifts. For example, here, this Lyman alpha absorption line at 2.2 has a corresponding silicon, another silicon line, not the same silicon line as these 2. So it has another silicon line over here. So this is how they actually identified all of these 49 absorption lines. And if you have followed such a long time, you probably start to think, where the hell is the mystery, right? Where's the mystery? I haven't talked about that. So the mystery is that despite they identified all of these lines, they actually didn't know what specific object is causing these absorptions. That's being said, we know that there's something absorbing in the universe, but what exactly is causing these absorptions? They had no idea. So they immediately start to think, maybe it's caused by galaxies, because in the vast universe, what can we expect? Can we expect there's some other stuff? Or it's obviously the universe is full of galaxies. So it's caused by galaxies, maybe. So what they did, one astronomer from the previous group, and also one more astronomer, Lyman Spitzer, you probably heard of his name because the Spitzer Space Telescope just retired probably only a month ago, but time has passed so fast, so I'm not sure about that. But yeah, these 2 astronomers made a bold claim. They think, okay, this is perhaps caused by galaxies. And they published a paper. This paper is super short, and this is the second equation that I'm going to show tonight. So we're all done here. They assumed these are all caused by galaxies, so the number of the absorption lines should be proportional to the number of galaxies in the universe times the size of each galaxy. These two factors, if you think about it, is actually fairly easy to be constrained. For example, the number of galaxies, that's easy. We can just sit behind a telescope and start looking for galaxies all around us. And we can use that density to be representative to how many number of galaxies can intercept in the sightline. And also, the size of the galaxy doesn't seem too hard either. You can point your telescope to famous galaxies like M31, the Andromeda Galaxy, and calculate how large the galaxies are. So all of these two factors seems to be very easy to constrain. So they add all of the numbers together, and unfortunately, the numbers don't add up. So this causes two issues. So one is that either these galaxies, so all of the galaxies in the universe, are not the source of these absorptions, or the size of galaxies are actually larger than we thought. In this paper, they took the second approach, and boom, we started to, this is the invention of the circumgalactic medium, the concept of the circumgalactic medium. So imagine this is the galaxy that you see normally. You see in the fancy pictures, you see from press release all over the place. But in fact, there is a bigger, giant gas halo around every single galaxy. So that's why when we count the number of absorption lines, we actually found more. So to give you a sheer concepts of how large the circumgalactic medium really is, that we understand nowadays as we are here today, we think that the circumgalactic medium in radius is over 10 times larger than the galaxy itself. And it turns out also nowadays that we think most of the carbon and silicon lines are actually really belongs to the circumgalactic medium. However, many Lyman alpha absorption lines belongs to no one. They are just free floating in the universe. So the paper that we just showed kind of correct or incorrect in both ways. It turns out both of the possibilities of causing those absorption lines are real. So I'm not going to talk about the free floating Lyman alpha absorption lines because this is such a famous concept, and I'm sure in the future in this lecture series, someone will talk about that maybe, so to be continued. But let's move back to the CGM. So the CGM today, this is a statistics of how many papers being published that's related to the circumgalactic medium, normalized by the total amount of papers being published. So here is the invention of the concept of CGM. And since the invention, you can see that the people's interests are in a very steady and slowly growing trend. And in the past 10 years, we start to see a lot of people start to pay attention to the circumgalactic medium. Why? And to understand that, we need to understand what are the modern ways of studying the circumgalactic medium. So I here listed 3 kinds of major ways to study the circumgalactic medium. One is from the computer simulations, which our host tonight, Cameron Hummel, is the absolute expert on this. From observations, we have 2 ways. We either observe them from absorptions or we observe them from emission. And I'm going to introduce you in detail of how these 3 ways work. So from simulations, we basically use the supercomputers to study the physical processes that happens in the circumgalactic medium. There are certain advantages and certain disadvantages. The advantages is that they're not, so simulators are not like us, not like I am an observer. So they're not limited by the amount of telescope times, which is good. And you can also watch the physical process in motion. We can, because we can wait for a million years for a certain physical process to happen. And there's our abilities, they have the abilities to experiment. For example, they're interested in certain physical process. They can either put them in the simulation or take them out. And this is sort of the way how us astronomers do our experiment. And the disadvantages, however, is that despite they are not limited by the telescope time, they're limited by the capability of the computers. And also, as many of you probably know, to simulate the whole universe, we need a whole universe. So we can't just brutally simulate everything. We need to make approximations on certain physical processes. So the outcome sometimes is uncertain. We don't know whether it really gives us the correct answers or not. So these are the two sides. The second way of studying circumgalactic medium, as you are probably now being very familiar with, is through the absorption. So we have a bright sources in the background, and it gradually passes through in the universe. And since the universe is expanding, it at certain place, it will leave the absorption in certain wavelengths. The advantages is that the background sources we can choose. We can choose what sort of background sources we want. So they can be really bright. And sometimes we can even use the galaxy itself. So for example, you have a galaxy here and the observer at you. In between these two things, there's the CGM of itself. So when the light's being emitted, it also contains the information of the CGM of this galaxy. The disadvantages is that the bright sources are really rare in the universe. For example, for quasars, even though we now found about 300,000 quasars in the universe, but to find a correct one at the correct redshift and correct position on the sky, it is extremely hard. And matching absorptions with a certain galaxies can be tedious. We don't know whether this absorption for certain belongs to this galaxy or not, because there can be undiscovered galaxies somewhere else that's close by. And the last one that we do is through emission. So CGM, despite its nature of faintness, it can be seen in certain wavelengths. For example, here, trust me here, I will tell you this is a galaxy, even though I know it looks very crappy. This is the real observational data that we can get. And at certain wavelengths, so this movie moves along in wavelengths. At certain wavelengths, you see here is the emission. Wait for a second, it will show up here. And it belongs to the circumgalactic medium. So the advantages here is that we can really get a full picture of what's going on around these galaxies, because for example, for absorption, there's only one, we have only one sight line at one direction. We can't get a full picture. But here we can get a full picture. The disadvantage is extremely faint, and it requires the most powerful telescopes and the instruments. And here I would like to say that there are two particular instruments that are really helpful in pushing this field forward. One is the VLT. One is called MUSE on the Very Large Telescope, and the other is called KCWI on Keck telescopes. So these are all integral field units. What is an integral field unit? You take an image on sky. For every pixel, you see a spectrum, right? So the movie I just showed you is actually a part taken by the KCWI instrument. So the other annoying part for us is that we have our atmosphere. So for example, I just said the Lyman alpha emission line. Remember what the wavelength of that emission line really is? It's 100 nanometers, right? So it's here. For a lot of the spectral lines that we are interested in studying the circumgalactic medium, unfortunately, they all lie somewhere here. So they are all in the ultraviolet. And that you can see here that the atmospheric transmission is basically impossible. It's impossible for you to see something in this wavelength on Earth. So you can do two things. One is you can go to space by launching telescopes. For example, the Hubble Space Telescope is one of the major telescopes that we use to study CGM. The other one is to let these spectral lines move to the optical window here. How to do that? Remember the redshift. So we can we can observe very distant galaxies, and these galaxies have very high redshift, and then they will move into the optical band. Unfortunately, to do that, these sources are already very faint. So you can imagine the CGM will be even fainter. So we need the largest telescopes possible on Earth. For example, the Keck telescopes. And here I'm going to address some of the useful instruments for us. For example, this is a space telescope launched by Caltech and JPL 10 years ago by Professor Chris Martin here. And this is called Galaxies. It operates in the UV, and it had a lot of very nice discoveries on the circumgalactic medium. And also the same group of people by Professor Chris Martin, they are launching balloons. And there's a telescope hooked down there so they can get above most of the atmosphere to observe the UV spectral lines. Now for ground-based, of course, we have the Keck telescopes, two telescopes on Mauna Kea, and we also have the VLT telescopes. The MUSE instruments is on there. So what do we know about CGM now? So first, we know that CGM is extremely dynamic. This is both in the literal ways that it has a lot of gas moving all the way around, and it also is in the physical processes. So there are all kinds of physical processes happening. People propose a lot of different physical processes to explain one same phenomenon. So it's extremely dynamic. And we also have a lot of different, so this plot shows y-axis the temperature and axis in density. So on the axis, you have about 100,000, a factor of 100,000 spanning here. And in temperature, you have about 100 or 1,000 factors there. So this is from simulation, and you can see that CGM contains all sorts of elements, all sorts of ions, and all sorts of gas in different phases in this diagram. And we also know that the CGM interacts with both the galaxies and the universe. It's basically the portway of a galaxy. So there are gas accreted to the galaxy, there are gas falling from the universe to the galaxy to fill the star formation. You also have this gas being blown out by star formation to the universe or being recycled. We also know that it's probably more massive. The gas in the CGM is probably more massive than the galaxy itself, because there's a missing baryon problem that we know of, that if we count all of the mass that we can see, these are baryonic mass, not the dark matter. So if you count all of these matters we can see in the universe, it doesn't add up to the number of baryonic mass that we predict from the CMB or other cosmological ways. So people suspect that a large fraction of these missing baryons are probably in the circumgalactic medium, so they're probably more massive than the galaxy itself. And now it's time, we're approaching to the end of this talk, so shameless self-promotion time. How does all of these relate to myself? Of course, I study the CGM myself, so what is my certain area? What's my certain specialty? So first, I'm not going to talk about that, because, so remember this guy here, it's just for fun, right? So if he sees a bookshelf, he will take a picture in front of it, that we know from Google. He is actually my advisor's advisor. So Wall Sargent, my advisor is Chuck Steidel here in Caltech. And fun part, if we just go back to another 13 generations, we can all be traced to Isaac Newton, which is kind of cool. I'm just trying to show off here. But my research, okay. So imagine you have a galaxy in the center and you have background absorption lines. And each galaxy can contain basically, can probably have 2 corresponding background absorption lines here. But we are really interested in the whole sample of galaxies, right? For a single galaxy, we are interested in that. But if we can't learn the whole picture, we should probably, let me go back to the, we can probably go back and start to learn the whole statistical property of galaxies. That's just what I'm trying to do here. So for one galaxy, you can have 2 different absorption lines. But if you consider the whole galaxy sample, you can start to build a full picture of how the CGM really look like. And so this plot here, each line of the, each line in this picture is actually a spectrum, because we have a lot of sight lines in the background. So each one gives us an absorption profile. And if we just rotate this a little bit, let me explain in detail. The y-axis is the velocity, because for each spectrum, we can really study the velocity of the, we can really get the velocity from the spectrum. And the axis is the distance from the central galaxy. And this is, don't forget, this is a statistical sample. So this represent a lot of galaxies as a whole. So this first thing. And the second thing what we did is that instead of using quasars as a background, we use galaxies, because quasars are rare, and even though they're bright. But what if we just use faint but common things, like more normal galaxies? There are millions of galaxies that we can use in the universe. In particular, we have 3,000 galaxies in your sample. And if we match them together, we got 20,000 background satellites, which is a lot. And just to make this single plot. And we think from this plot that we can tell there is a combination of outflow and inflows going on. And would it be nice that, since these are from absorption lines, would it be nice that we can do the same thing to the emission? The answer is correct. The answer is yes, we can do this. And for example, here, as what I just showed, these are from absorption kinematics, and the right side, these are from emission, taken from the KCWI instrument. And we can do this, and also we can understand so by doing this, we can understand how photons interact with the CGM gas more clearly, because you can immediately tell these have very different profiles, very different shapes. So to give you a summary, I'm ending my talk here. The galaxy that we know certainly is not a full picture of how a galaxy should be. And also, astronomers finally start to have tools to study all of them in details, especially in the past 10 years, because we started to have powerful computers and also powerful telescopes that are just enough for us to start explore the CGM in details. We know that CGM nowadays, we know that CGM is dynamic and massive. And also because we just acquired enough instrument, enough tools, enough toys for us to play around, this is still a developing field. So if you're interested, stay tuned. There will be more news coming. And thank you for your attention.
Excellent work, Yuguang. Thank you very much.
Thanks, Cameron.
All right, so we've got some great questions from the YouTube audience, and we're going to go straight into, can you unshare your screen?
Yeah, sure.
Okay, great. We're going to go straight into our Q&A panel discussion. Can everyone, let's see, does Does YouTube see all of us? Sorry about these technical difficulties here. Okay. Okay. So everyone should now be seen. All 6 of our panelists. I will introduce everyone. You guys just heard from Yuguang Chen, who's a PhD candidate who specializes in his research in the circumgalactic medium and the evolution of galaxies using the largest telescopes in the world. I'm Dr. Cameron Hummels, a postdoctoral researcher in the department who primarily uses computer simulations to model and simulate galaxy evolution, including the CGM, what Yuguang was just talking about. We also have Nicole Wallach, who's a PhD candidate in planetary sciences at Caltech, who uses space and ground-based telescopes to study the atmospheres of planets around other stars and try and understand how planets form and evolve. There's Keisha Day, who's a PhD candidate in the department who uses optical and infrared telescopes to find and study cosmic explosions and to understand their formation, the formation and fates of dead stellar remnants in distant galaxies. We have Anna Ho, who's a graduate student who investigates the violent deaths, the death omens, and the afterlives of stars. And finally, we have Michael Zhang, who's a graduate student who studies the atmospheres of planets around other stars, particularly small rocky planets. So welcome everyone to the panel. Let's look at what was asked in our questions. So Yuguang, some of the questions that people were asking,
Right.
you addressed this in the talk, but I just want to make sure that we cover it fully. How does so much carbon and silicon gas and dust get into the CGM? And what's the particle density? And how many solar masses? All of these questions.
Okay, cool. So first, we are not very sure about dust yet because observationally, we're still trying to look for the evidence whether dust exists in the CGM. There are evidence that supports it. There are evidence that disagree with this existence. So why? Why there are so many these sort of different elements? So when the universe is born, there's only hydrogen and helium. But we all know that there are a lot of other material, a lot of other elements. For example, carbon, that's what we are made of. There are silicons, that's what the Earth is made of. So it's basically because of the galaxies themselves. The galaxies, because star formation is basically a giant factory of producing all of these elements. So for example, carbon, silicons, the elements I just mentioned, these are also the star formation, the star made themselves, and also the supernovae. They will make a lot of elements. So how do they go into the CGM? Remember, there's outflows. So when the star forms, or when they die, they blow up these massive wings, and some of them can actually be powerful enough to blow the gas inside the galaxies into the CGN, or even further into the universe, what we call the intergalactic medium, IGN. So this is where these elements, heavy elements, are actually coming from, aside from hydrogen and helium. And what's the other question? You're muted. Oh, what's the mass, right? We don't know for sure yet. So again, this is a developing field. There are, so many of the plots here I show are from a review paper published 2 years ago. And I really love one of the figure that they show how much mass can be attribute to the CGM, and the error bars are way around all over the place. So we don't know exactly how much the mass is in the CGM. We have some ideas. It can be ranging from, for example, so we have about 90%. How much missing baryons are there? 90%, is that right, Cameron? I can't.
The missing baryons in individual halos?
Yeah.
No, it's not that large, but
yeah, these CGM can make up to the most 100% or even 120% of the missing baryons, but 50% or 30% of that is the lowest estimate. So we really have no idea.
Right. So on the order of 1 billion solar masses for our Milky Way galaxy, on that order, which obviously is quite a lot. Other questions? Okay, so this is relevant to what you were just talking about. When trying to detect absorption lines of elements, how do you know if a dip is due to one element or another element? Either could be shifted by large amounts and land in the same place. And related to that, how do we know if a particular element causes absorption at a particular redshift? So how do you disentangle if you see a dip here? Is it due to hydrogen or silicon or carbon, and at what?
It can be a variety of lines, correct. That's a very good question. And as I showed, so partly as I just showed, we can find, so if we suspect this line, for example, is caused by carbon because of this very signature doublet feature, if we suspect it's caused by carbon absorption, we can calculate a redshift from it because we know the emitted wavelengths from it. And then we can look for other possible absorption lines caused by, for example, silicon, hydrogen, possibly magnesium, other lines. So of course, for a certain wavelength, there are probably 100 or 1 million possible candidates that you can think of that can cause the same absorption line if you just check the database. So you need to have some sort of a sense of what is possible. For example, there are different ions can cause different absorption lines. For example, carbon, there's a carbon-2 and carbon-4. Carbon-2 means it's singly ionized, so 1 electron has escaped. That's carbon-2. If 3 electrons escaped, that's carbon-4. And there are also higher orders like oxygen-6. So you need to have a more some sort of idea of what is more possible. For example, lower ions are probably more possible than the higher ions, and and also the other sort of stuff. Of course, we can't always be 100% certain. So for example, all of Lyman alpha absorptions in the Lyman alpha forest, in many cases, as I said, it's very tedious to associate one absorption to a galaxy because there's so many possibilities and you are not even sure you have accounted for all of the possible galaxies there. So yeah, it's a challenging, and the way we're doing this right now is we do it statistically. So for example, you have a galaxy, find how many absorptions are there around it, and look for other galaxies and count. So you have a sense of how many, on average, how many absorption systems are there around a galaxy. Some of them can be attributed to the background. That means they're from the universe itself. So yeah, that's a very good question.
Cameron, could I comment on how we do this for stellar explosions?
Absolutely, that would be wonderful.
So Yuguang's been talking about spectroscopy of very distant galaxies, but other astronomical systems that you can do this for are the explosions of stars. And that kind of cosmic forensics is something that I work on and something that Kishalay also works on, so he can comment on it as well. But when we get one of these explosions, we also use big telescopes to take spectra. And what we're trying to figure out is what the star was made of, the star that exploded, what it was made of. And in that case, the identification of lines is complicated because the line is moved not only by the expansion of the universe, but also the expansion of the explosion material. So the explosion happened and all this stuff is going out like this, and that actually shifts the lines as well. So I could show you, if you'd like, some supernova spectra. I have some
That'd be
open here.
awesome.
Can I share my screen?
Yeah, absolutely.
Okay. So this is some from an explosion that's happening right now that I've been working on. So can you see this?
Yes.
Okay. So the number here tells you how many days after the explosion it is. And the so this is 11 days, this is 12 days, 17 days, and so on. And so I'll center this over here so you can kind of see how this works. So this line, this line here is calcium. And you can see that over time, this line actually moves. So at 17 days, it's over here. And then at 25.7 days, it's kind of over here. And it's scooting more and more to the right. And that's because the explosion is slowing down over time, as we have calcium and silicon and iron. And so we can use the identification of these lines to track not only what the star was made of, but also how the explosion itself is unfolding and how fast all the material is being thrown out into space.
Very cool. Very cool. Thank you for tying this into a different area that's not just the CGM, because there's obviously lots of aspects of astronomy that this spectral identification and orientation applies to. All right, I'm going to put the CGM questions on pause for a moment to make use of the rest of the panel. So we had a bunch of questions on social media over the last few days. And one of them is, if Earth has its magnetic fields because of its molten metallic core, then what makes the magnetic fields around Jupiter one of the strongest in our solar system, and being a planet that's composed of merely gases? Would any of you like to take this?
Yeah, I got this. So yeah, the whole reason why the Earth has a magnetic field is because of this molten magnetic core. You have this convection of this molten metal. And it's really similar actually with Jupiter. So it's not a like molten metal, it's gas. So you can have metallic hydrogen. It's just a form of hydrogen that also conducts electricity. So it's very, very similar. It's just you kind of have this fluid in the Earth, or you have this gas on Jupiter. And it's basically fundamentally doing the same thing. It's convecting. You have this movement of a thing that can conduct electricity, and that's what's going to generate your magnetic field.
Awesome. Excellent work. Thank you, Nicole. Okay. Another question. Here's a good one. How does dark energy impact the expansion rate of our cosmos? Michael, would you be interested in taking this?
Yeah, sure. So for those of you who don't know, dark energy is something that pervades the entire universe. So we call it dark energy because that's how it acts in the equations. It acts as if it's a form of energy that has a constant energy density. So a constant number of joules per cubic centimeter, no matter how much the universe is expanding. So in the very early universe, when the universe was small, we had a small amount of dark energy. In the far future, when the universe is very big, we will have a huge amount of dark energy. And the effect this tends to have on the universe is that it acts as a sort of anti-gravity. So instead of pulling the universe back together, it tends to drive the universe apart. And it actually drives the universe apart exponentially. So the universe will get bigger and bigger in an exponential way. Eventually, all of the galaxy clusters that we see at billions of light years from us will disappear from the field of view. Because Yuguang talked about the redshift. Well, the redshift of these galaxies is going to go down exponentially. And eventually, they're going to be way too faint and be emitting a way too long of a wavelength for us to detect. Incidentally, the cosmic microwave background which is a leftover radiation from the very early universe, when the universe was still a uniform hot gas at 5,000 degrees. Well, that radiation is also going to be redshifted until it's invisible. So for people in the far future, they're going to look out into the universe and see essentially an empty universe with only a few galaxies and no evidence whatsoever of how the universe came to be. So yeah, people in the very far future will probably not be able to come up with the Big Bang Theory on their own.
Yeah, that's pretty interesting. That's very interesting that we live at kind of a special time in the universe right now.
Mm-hmm.
Okay. Here's one for Kishaloi. If F equals ma, that is to say force equals mass times acceleration, then comet impacts should crack tectonic plates because their impact speed is greater than Mach 30. Okay, kind of a strange question, but what do you think, Kishaloi?
Right, thanks. So yeah, that's a great question. I think so. The point here is that yes, there is a lot of space stuff out there. There's a lot of rocks floating around in space, and they keep colliding into the Earth all the time. And in fact, if you took one of those pieces of rock and you just allowed them to drop to the surface of the Earth without anything else, they would crash into the surface of the Earth at what is known as the escape speed of Earth, which turns out to be about 25,000 miles an hour. But it turns out the saving grace for us is that there is an atmosphere between us and those rocks. And when these rocks tend to fall into the atmosphere, they get burnt up because of friction between the rocks and the air that is in the atmosphere. And as it turns out, given the sizes of the rocks that are typically there, most of these rocks never make it to the Earth's surface. They just burn up 100 kilometers above the surface of the Earth. So you never see them. But that's not true all the time. In fact, there are big rocks out there. There are comets, and comets are usually and bigger asteroids. And when they do end up surviving the path to the surface of the Earth, they can create catastrophic explosions. The most famous of which is the rock that crashed into somewhere around the Yucatan Peninsula near the Atlantic Ocean, and that is believed to have caused the extinction of the dinosaurs, where the idea is that you had this big piece of rock, which was so big that the atmosphere couldn't do anything about it. And it crashed into the surface of the Earth, and this entire crash, it spewed a lot of material all around the Earth. And this spewed material caused major climate changes around the planet, which led to the extinction of the dinosaurs. So yes, those things do happen, but they're rare, and the atmosphere is a saving grace for us as a species.
Yeah, definitely true. Or even the potentially larger impactor that's referred to as Theia, the one that struck the proto-Earth in the early part of the solar system, and according to the impact hypothesis, birthed the moon out of part of the interior of the Earth. I mean, clearly that was such a massive impact that it definitely penetrated, not just the tectonic plates, but also the entire crust, delving into the mantle. But fortunately, that's a once every 5 billion year kind of periodicity. So hopefully we don't have anything else like that flying around that could strike us. Thank you, Kishaloi. Let's see, what's another good question? What do you all think about the Fermi paradox? Michael, do you want to handle this one?
Okay, sure. Yeah, so I really like speculating about aliens, and that's what the Fermi paradox is about. So it's like one of my favorite questions. Okay, so for people who don't know, here's the Fermi paradox. Why haven't we met aliens yet? Now, some people will say we have already met aliens. We see plenty of UFOs, but okay, they're UFOs. They're unidentified flying objects. And as far as I know, there's no convincing evidence that any of them are actually aliens. Okay, so the Fermi paradox is, assume that humanity has a bright future ahead of us, right? We'll colonize the solar system. We'll colonize billions of other planets. On each of those planets, we'll have a population of trillions of people. We'll have easy Star Trek-like interstellar spaceflight. We're going to mine the asteroids. We're going to harvest the energy of entire suns and use it for our civilization. Well, if we do that, then anybody anywhere in this galaxy should be easily able to detect the existence of our civilization. Because number one, they'll see entire stars disappear as we engulf them with Dyson spheres to use their energy for our purposes. And number two, we'll be sending explorers and scientists and ambassadors and geologists like all over the galaxy, interviewing the natives, sharing our knowledge with them, trading with them. Obviously, this hasn't happened because we don't see any alien ambassadors. So why is that? Well, so you can imagine a whole number of solutions. And actually, if you want a really exhaustive overview of this, spanning like many, many hours, go on YouTube and check out Isaac Arthur. He's a fantastic YouTuber. He's very grounded in the science, but while staying grounded in the science, he's very good at exploring possibilities and speculating. Right, so one possibility is, we are the only civilization in the galaxy. That's entirely possible because we have no idea how common intelligent life is. It could easily be, one intelligent civilization in 10 to the 20 years, a rise per galaxy. And if that's the case, then we're almost definitely the only civilization in the galaxy. Another possible civilization is that, well, when you develop technology, you inevitably kill yourself. So, for example, maybe nuclear war is just so likely and so inevitable that eventually we're going to have it and all humans will die. And then our civilization will be extinct. Or maybe the aliens know of us. So maybe there are many aliens and they know about us, but they're keeping us in a zoo, right? They don't want to disturb us until we discover, faster than light travel. And then and that will give us the technology to go out into the galaxy and discover the aliens for ourselves. So there's many, many possibilities. I guess the last thing I'll say about this is that I don't find the apocalypse scenario to be too probable. Because, for example, in human history, many civilizations have collapsed. But after they've collapsed, first of all, it's never a global collapse. This civilization collapses, but the other one on the other side of the world is flourishing. And second of all, the collapse is never permanent. So Rome fell, right? Rome collapsed in 500 AD. But if you go to Italy today, there's a city called Rome, and it's bigger, and it's richer, and it's more populous, and it's basically better in every single way than the Rome that collapsed. So I don't think any apocalypse can really wipe us out.
I have a couple of points to follow up, if that's okay.
Mm-hmm.
Yeah.
So I think there's been a couple of different kind of interesting trains of thought that this has had and spawned. And one is the Drake equation, which I think is also a really interesting thing. So for those of you who don't know, it's just basically an equation where some of the variables are known, some of them are unknown, number of planets around stars, number of stars in the galaxy, things like that. But then it's also the likelihood of intelligent life evolving. So basically it's the number of intelligent species that could exist. That's pretty much what the Drake equation is. So it's kind of interesting to see some people speculate wildly on some of the less determined factors in that equation. But also there's been some very interesting sort of astrobiology work that's been done, Michael, on kind of similar sort of what would a world look like that had destroyed itself. So things like if a planet had killed itself from some nuclear holocaust or something like that, you would expect to be able to see that fact, like that in its spectrum, basically, is the idea. So there's been a lot of interesting work that's come out of a lot of this astrobiology stuff, purely based on speculation, kind of on things in that vein of, okay, let's say the species did go extinct for some reason and all the intelligent life on a planet doesn't exist. Could we even determine that? And it seems like depending on how it destroyed itself, the answer could be yes. So I think it's kind of an interesting route that a lot of the wild speculation has taken.
Yeah, this might be the paper you're mentioning, but like there was a paper asking, can we detect CFCs in the atmosphere of a planet that destroyed itself? CFCs being, the refrigerants that we used to use that like are really bad for the ozone layer, but we stopped using them. And the answer is yes, but only if the planet orbits a white dwarf.
Yeah, so there's a couple of different kind of extreme situations. One of them is that, yeah, a lot of Lisa Kaltenegger's group at Cornell has done a lot of work on this, just off the top of my head. Yeah, so definitely I've seen ones that are nuclear fallout and it completely shrouds the planet. What would we see? So there's been a lot of really interesting routes that's gone, I think, instead of just wildly speculating and things like that. But I think that's kind of cool that those wild speculations do drive science sometimes for a lot of our parts of our field.
Mm-hmm.
Excellent. Thank you, guys. There was a question last week. How does rotation direction affect a galactic merger? I.e., if Andromeda rotated the opposite direction, would the merger with the Milky Way look differently? So this is a really a good question that I like a lot because it ties in with a lot of what I kind of work on. So 2 weeks ago when we had our presentation by Jason Wang, there were some questions related to the merger between the Milky Way galaxy, our galaxy, and the Andromeda galaxy, because they're on a collision course and they'll merge in about 5 to 8 billion years from now. And so I showed a movie. I think that's what this question is referring to. I showed a movie, so I'll share my screen here. You guys see that okay? Galactic mergers. So this is the video that I showed last week or 2 weeks ago. And I'll just show it again because it's a really cool video. This is a simulation that was done by some of my colleagues in the field. The PI of this project was Roland Vandermeerel, who's at Space Telescope Science Institute in Baltimore. And this is a simulation showing in the upper right, you've got Milky Way. In the lower left, you've got Andromeda, and they are going to merge. And you can see the time in billions of years in the lower right. And as they get close enough, they merge, albeit slowly, and their disks that are composed of gas and stars takes on these peculiar, what are called tidal features, tidal tails. Tides just means gravitational features, basically. So tidal tails, tidal bridges, and eventually they merge together to form what we call, or what we're going to call, Milkomeda, because it's composed of the Milky Way and Andromeda. Now, this simulation was done in the last 10 or so years, but historically, astronomers looked up in the sky and they saw these weird looking galaxies. This is called the mice because it looks kind of like cosmic mice that are playing. And we weren't really sure how you could form these really bizarre galaxies. So we just referred to them as irregular galaxies and kind of threw up our hands and didn't really know what to do. But there were two brothers in the 1970s, Alar and Yuri Tumre, who got a hold of some of the first computers to try and simulate these sorts of mergers, or simulate what happens when galaxies run into each other, to see if it could explain these really strange looking systems like the mice. And because these were early computers in the 1970s, they were very, very simple. And this is, you can see essentially frames from one of their simulations. The two solid black dots represent the center of mass of two galaxies that are passing in what's called a parabolic orbit next to each other. So their path traces out a parabola. And then around the leftmost of those two galaxies is a bunch of test particles. So those particles that are just the empty circles represent massless particles. These are particles that just trace, they orbit and trace the potential. They don't interact with their surroundings. They just trace out the trajectory that something would have if it had no mass. And initially in this particular system, it's called a retrograde collision, because the rotational direction, i.e. the spin direction, is the same direction as the, oh, wait, this is retrograde, my mistake. This is a retrograde collision where the direction of the rotation is opposite the direction of the orbital trajectory. And you can see, if you look from time frame to time frame, from -1 to 0 to 1 to 2, that essentially what happens when this passage takes place is that the external system perturbs that disk of stars and gas as it passes, but it does so quickly that it's only an impulse, and it doesn't actually, it only kind of shocks that and makes it bounce around, as you can see over the course of this time series. In a direct passage where the rotation and the orbit are aligned, you get this behavior. So the spinning direction of the individual particles in that disk is the same, but now the orbits are flipped. So it's a direct passage and they're aligned. And what you can see is the particles in the disk that are closest to the secondary body get tugged, and they continue to get tugged by that body as it passes by, and it yanks those particles right off, and it forms what's referred to as a tidal bridge in between those two objects. And you can see that it looks somewhat like the features that we were seeing either in the mice image that I just showed or in that simulation that I showed. It correctly explains why we see these weird features. And in fact, it's a very simple system. It's just having two galaxies that are passing next to each other. So this is a really cool simulation that was done, again, about 10 years or so ago, of a very simple system of these two galaxies that are rotating. And periodically, as it just did, it'll stop the simulation and show what an actual Hubble Space Telescope image looks like of a particular system, and show that this very simple simulation of two simple disks that are slamming into each other can correctly predict and visualize a lot of these different galactic irregular systems. So yes, they look funky and they look weird in the sky, but it turns out that this is just a very common thing, and it's just due to the presence of gravity in rotating systems when they collide with each other. And it's also awesome because you get to see how well it works and how beautiful some of these these Hubble Space Telescope images are. Sorry, I'll just let this play out because it's super cool. Okay, that's it. So yeah, so in answer to the question, the original question, yes, the rotational direction of the Milky Way and Andromeda relative to their actual orbits does influence the structure that comes out of it. Eventually, because they're gravitationally bound, they will acquiesce into a single structure regardless of the rotation. But in the intervening 2 billion years between their first passage and when they finally coalesce into a single structure, you'll have very different behavior if they're co-aligned or if they're counter-rotating, as we just saw. Okay, let's see, another question. We'll ask some more. There were a bunch of CGM questions, so I'll throw Yuguang to the wolves here. How much does the gas around galaxies affect the spin of spiral galaxies? This is an interesting question, relevant to a lot of, relevant to a lot of recent research that's going on. It appears that circumgalactic media of different galaxies does have a net rotation in general. And oftentimes that net rotation is aligned in some ways with the rotation of the disk if it's around a disk galaxy, but it doesn't necessarily appear to be the same rate. This is usually traveling at a slower rate than the disk is, as you might expect, because there's a lot more angular momentum out here. So even to go slowly, it's carrying more angular momentum. So it appears to be a continuous shift from the disk that's spinning quite quickly out to the halo. But it's not entirely understood why that exists. Yes, there's a continuum of behavior between what's going on in the halo and what's going on in the disk, but the CGM has a lot of mysteries, which is why people like Yuguang and myself are actively researching it to better understand. And part of that is the rotational behavior of it.
Can I add
anything to add, Yuguang?
Yeah. This also relates to how the age of the galaxy itself. So when you're looking at a younger galaxy, the galaxy itself doesn't have a well-defined rotational axis or a disk that you normally see in the present universe. So at that point, it would be really hard to associate the rotation of CGM with the galaxy itself, because both of them are not well defined. And also the rotation of the galaxies for the younger galaxies heavily influenced by how the accretion flow is falling onto the galaxy, because it's more back in the day when the universe is a lot younger. The universe itself is much more much more active, and you have much more materials to accrete with. So this is a very good question, and we don't have a clear answer to that.
That's fair. Related to the talk, one of the question was, is there any specific reason behind getting the Lyman alpha line near 100 nanometers?
Atomic question. This is, yeah. So it's basically related to the atomic physics. First, Lyman alpha somehow, so I would say that it's probably the most, you have the strongest interaction between the hydrogen atom, which is the most common atom in the universe. So the strongest interaction between matter and photon is connected with Lyman alpha. In many senses, connected by the Lyman alpha line. So it's in both emission and absorption. And it's emitted by hydrogen atom because, so in the way that the hydrogen atom have different levels of, so electron around the proton that makes up the hydrogen atom. And this electron has different layers of orbits. And one of the layer that's just above the ground state is, this transition corresponds to 121 nanometers. And this is exactly why this Lyman alpha, this is called Lyman alpha transition, because it's the first alpha transition. It's very strong because most of the hydrogen, if it's in the neutral state, it will be in the ground state, and you have less hydrogen atoms on the n equals to 1, this slightly elevated state, and then you have even less. So this is why we are very interested in this line, and it's also why this line unfortunately falls in the ultraviolet.
Yes, thank you.
Yeah.
Okay. Another question. What planets in our solar system are actually native to our star system? How many, if not all of them, have formed together as one intact star system? Which, if any, are from extrasolar origins? How did the composition of the planets, including the inner ones, especially Earth, confirm or question that presumption? It seems like a good question for Nicole.
Yeah. So actually, from our understanding, all of our planets formed in our solar system. So kind of the way planets form and evolve, they form from this gas and dust rich disk that surrounds a star. So kind of when a star forms, it has this gas and dust around it too. So what happens is the gas and dust around the star, you have the star, and it forms this disk around it. And that disk is actually what planets are formed of. It's this combination of gas and dust. Basically, you'd expect it to have a similar composition to that star because it came from the same sort of cloud of material. So the different planets kind of form in different ways, but we all expect them to have formed within our solar system because the kind of dynamics of acquiring a new planet would be kind of hard for one, but also you need to have a planet that's close enough, has dynamics enough that would kind of get launched. You do have some rogue planets, these planets that were ejected from their solar systems, these free floating planets, but none of our planets we think were acquired in that way. And kind of the way that we're thinking about the inner planets versus the outer planets, they were formed differently. So you have this sort of compositional difference between the rocky planets that are interior and the outer gas giant planets. But that all kind of ties together with what we'd expect from how planets form and evolve. So for example, these gas giant planets actually formed before the rocky inner planets that we have. So you have this timeline kind of when planets formed, and that is also imprinted in the composition of the atmosphere. So for example, Jupiter, the biggest planet in our solar system, has the largest gas envelope. In order to actually be able to get all that gas onto the planet core, you need to still have gas in the system, right? So we don't have tons of gas just around our sun right now, meaning that that gas had to have been accreted, had to have been gotten attached gravitationally to whatever rocky core is in the center of Jupiter when there was still gas in the disk, which is about 10 million years, we assume that gas dissipates. So you do have this kind of compositional difference, which does imprint how the planet formed. So there's actually a difference in the atmospheric compositions of the gas giants in general. So the smaller gas giant planets, Uranus and Neptune, actually have more metals in their atmosphere than Jupiter and Saturn do. So metals being, for an astronomer, metal is anything that's not hydrogen and helium. So I'm in a geology department, so when I say that, the geologists get a little bit mad at me. But to an astronomer, anything that's not hydrogen and helium is a metal. So you have these metals, which could be oxygen, could be nitrogen, things like that. So the way that they're accreted is just through solids. So you have this solid accretion onto these smaller gas giant planets, and you have more of that basically. So you have this late stage accretion of solids. So you can kind of probe what the accretion history and the formation history of these planets are by looking at kind of the compositional fingerprint, the atmospheres of these planets. So you look at the rocky planets, they had to have formed later is the thought, because they didn't have enough time to acquire a large enough central mass to start accreting gas onto them, at least not enough to have these huge gas envelopes. So all of that ties together though. So the planets in our solar system kind of, we assume make sense and kind of do inform our knowledge about extrasolar planets. But the more we learn about extrasolar planets, the more we realize that our idea about planet formation isn't complete, because we have these planets that are we don't have in our own solar system that are really, really common out in other solar systems. But we don't expect any planets to kind of come from other places, really, because it all does tie together. And you have these really wonderful dynamical simulations that have been done for our own solar system. And you have these dynamic simulations that are done for extrasolar planets. So kind of what we're seeing observationally is that if solar systems are acquiring planets from other places, we're not seeing it, or we're not seeing the observational evidence of it.
Yeah, I have something to add to that, which is, so Nicole said the planets of our solar system form in a disk. And the way you can see that is if you look at the orbits of the planets in our solar system, they're all in the same plane. So actually, so at the beginning, Cameron showed a stellarium model of today's night sky. And if you pay close attention and you look at the 3 planets that he showed, they're in a line. And that line is called the ecliptic. And that is the line along which the disk formed, the disk that gave rise to all of the planets.
Excellent. Thank you for pointing that out. Yeah, great answers, guys. Great answers. There's a question from an 8-year-old, Penelope. I think this is in reference to what I was showing before with the simulations. What happens if a galaxy collides with 2 already collided galaxies? And the answer is that that's what's happening constantly through our universe. And I have a really cool movie to showcase that. Because really, as a simulator, my bread and butter is running computer simulations, but then visualizing them because it looks really cool to look at some of these simulation movies. So I'm going to take advantage of that. So can you guys see this movie, hopefully? So this is a simulation that colleagues of mine created. It's called the fire simulations. It's showing the evolution and the formation of a galaxy, much like our own Milky Way galaxy, but this starts long, long ago, just after the Big Bang. On the left side of the movie, we'll see the distribution of matter, primarily in gas in this case. And then on the right, we'll show the temperature of that gas. And so as it moves forward, the white circle represents the area of influence of a particular galaxy. Now, there are lots of little galaxies that are forming here, and they're falling into the primary galaxy, the one we're studying here. All these little clumps of gas are galaxies unto themselves. And as they fall in, they merge. So yes, some of these smaller galaxies may be the products of themselves, be former mergers of other systems. And this, we refer to it, it's a little bit morbid, it's called galactic cannibalism. So galaxies are constantly eating their neighbors and growing and getting bigger and bigger and bigger. And as they do so, that's the evolution of these systems. The right, this is a little bit deeper, talking about how the cool gas eventually forms stars, and then those stars turn into supernovae. And so you have these hot yellow plumes that are shooting out as supernovae are ejecting their hot material. But the long and short of it is that galaxies grow through colliding and merging with other galaxies. But that's a great question, Penelope. Thank you for giving me a chance to introduce all of that stuff. Let's see, where were we? Another question. Do any of the telescopes in the growth network, growth is an acronym for Global Relay of Observatories Watching Transients Happen. It's a collaboration that is all around the world, but it's headed by Professor Monty Kosliwal, who's a professor at Caltech. So do any of the telescopes in this growth network work on the CGM? We have some growth people here.
Yeah.
Yeah, both Kishalay and I are members of growth, so we can probably address that.
Would you guys care to respond to this?
Sure. Well, first, maybe I'll provide a bit more context for people who don't know what growth is. Can everyone see my screen?
Yes.
Yeah, so for some context, so what are transients? So transients are things that appear and disappear in the night sky, so they're not there all the time. And so that includes the kinds of cosmic explosions that Kishalay and I study. And the problem with trying to watch one of these explosions unfold from here on Earth is that the Earth spins around. And so for part of the time, no matter where you're observing from, usually your view of this explosion is blocked. And so the idea with growth is that we work together kind of like a relay team. So we have colleagues working, contributing their telescope resources all over the world. And so when the sun rises on one partner in this network, it's setting on another. And so we can sort of pass the baton on and get continuous observational coverage of one of these explosions. So that's what growth is. And so I guess the question is, does growth make any observations of the CGM? And I can address one way in which the observations of these kinds of cosmic explosions can teach us about the CGM. So the CGM, as Yuguang was explaining, is basically a bunch of gas and dust and material lying around. And Yuguang was sort of talking about there being a galaxy in the background that's shining through the CGM. And then by looking at the light from that background galaxy, you learn about what the CGM is made of by looking for spectroscopic lines. But the light, the sort of backlight that you're using to study the composition of the CGM, that can be almost anything. So you could be a galaxy, but it can also be one of these explosions. And some of these explosions are particularly excellent as tools to study the CGM because these are the brightest phenomena in the universe. And so an example is gamma ray bursts, which are energetic jets of matter that are launched, we think, in the birth of a black hole. We can see those basically to the other end of the universe. And so you can use them to study all the material along your line of sight to that explosion. So, and that's something that I work on. So through growth, one can study the CGM sort of indirectly by studying some of these distant explosions.
Excellent. Thank you.
Can I just add very quickly? I should
By all
also
means,
say,
sure.
aside from optical ways of the background sightlines, background objects as the sightlines, you can also use radio. For example, you can use pulsars. And very recently, there are also people using fast radio bursts. So it can really be anything.
True, true.
I can add something real quick to that. So, is that okay? Yeah, okay.
Yeah, sure, go ahead,
So,
please.
yeah, as Anna was mentioning, both Anna and I work on all kinds of cosmic explosions. And so far what you've heard of is about all of the gas that lives out in the outskirts of galaxies. But as it turns out, when two galaxies collide with each other, they also end up spewing out a lot of matter into the outskirts of galaxies. So what that means is that when you look at a galaxy, there's not only gas in the outskirts of galaxies, but there's also all kinds of mass over there. These are all very old stars that have been thrown out by these galaxy mergers when these mergers were gravitationally pulling off matter from the individual constituent galaxies. So you'd expect that if some of those stars actually live over there, then eventually, as we see with other types of cosmic explosions, the stars that live in the outskirts would also eventually explode and produce the same kinds of cosmic explosions that we see. And in fact, that's exactly what we see in when we look for these explosions in the universe. We see that there is a small but noticeable fraction of supernovae that actually happen in the outside galaxies. Even though most of the stars that we know of live inside galaxies, all these galaxy mergers, they end up throwing all kinds of stars into the outskirts of galaxies, and we find them when they explode. So maybe I can show one quick example. So well, one of the most prominent examples of this is the fact that when we look at nearby galaxy clusters, we actually see explosions happening in those galaxy clusters. So wait, do you see my screen?
Not yet. It says you've started sharing your screen, but it just shows blackness.
Okay, let me check something. One moment. Right. How about this? Is that...
Yes.
Yes.
We can see
okay,
the upper left corner of PDF.
Oops, sorry. What am I doing? Okay, sorry about that. Okay. Yeah, this may or may not work, but I'm still okay.
You're still showing a Shree's paper, actually.
Okay. So okay. Okay. Never mind. So yeah, the point is that yes, there is not only gas in the outskirts of galaxies. There's also stars living in the outskirts of galaxies, and we actually find them with networks like GROWTH that allow us to follow up supernovae very rapidly and understand what kinds of stars live in these outskirts of galaxies that is coexisting with this CGM around galaxies.
Yes. Yes. There's a bunch of stuff out there. A bunch of stuff. Thank you. One of the questions is, any new information or anything interesting about Comet Atlas or new technology that helps us learn more about comets?
I can say something quickly about that.
Sure.
Right. So yeah, there's been some really exciting developments on Comet Atlas. So just for to remind everyone, so Comet Atlas is this comet that has been approaching the inner parts of the solar system, and it's become substantially bright. So it's pretty bright right now, and it was expected to become a naked eye object when it was getting supposed to get closest to the sun. And it would have been quite spectacular because you would have been able to see it quite clearly in the night sky at the time when it was supposed to be brightest, except it turns out that recent observations from telescopes around the world seem to be showing evidence that it has started disintegrating. Now, what that means is that the comet, which is this, a comet is effectively a ball of ice and dirt. And when it approaches the sun, what you see is that this ice and dirt gets heated by the light from the sun and starts melting. And it is exactly that melting that produces the spectacular tails that give comets their name. Now, in extreme cases, what can happen is that the radiation from the sun can heat it up so much that the ice actually starts melting so much that it starts breaking up. And that is exactly what we are seeing in the case of Comet Atlas right now, which is that when you look with big telescopes, you see that the comet is not a single piece anymore. It has now started developing two nuclei. And what that means is that depending on how quickly it disintegrates, it may not actually brighten up as significantly as we were expecting it to, but it might actually disintegrate before it actually gets to the point where it was supposed to be really bright. So yeah, I think that's the main development on that front.
Yeah, I'm confused. I've seen a bunch of stuff about Comet Atlas, but also Comet Borisov. Are they one and the same, or are they two separate comets?
Those are two separate comets. So Comet Borisov is another completely exciting development because it's one of these interstellar comets, which means that it's a comet where we can measure the orbit of the comet, and we know that the comet did not originate inside the solar system. What that means is that the comet is moving so fast at this point that once it passes the sun, it's going to completely leave the solar system. It is traveling fast enough that it's not gravitationally bound to the sun. So Comet Borisov is actually the second known interstellar comet after the first one that happened last year. But yes, so those are two different things. And Comet Borisov itself, is doing quite a lot of spectacular stuff as well. And there's a bunch of people around the world who are trying to follow it up.
Right, and it's also, I was reading, is also kind of falling apart, and chunks are drifting off, and it's unclear if it's drifting off because it's rotating so fast that it's spinning pieces off, or if because there's, as you were saying, there's pockets of volatiles in the interior that are heating up and then blowing stuff off or whatnot. But it's super exciting stuff.
Right. The Hubble Space Telescope, in fact, has been observing Comet Borisov quite frequently because Borisov is a really rare type of comet. There are very few, this is only the second known interstellar comet known. And in fact, Hubble Space Telescope observations now appear to be showing that it's throwing off all kinds of jets. So these are these streams of material that are coming out of the surface of the comet because the heat from the sun is melting the comet, literally melting the comet. And it may or may not survive the journey through the solar system, but we'll have to wait and see how that goes.
Right. No one is proposing that this is aliens in the same way that they did with the last object, I presume. Has anyone? I mean, I haven't read anything, but
not that I know of yet.
People like to invoke aliens.
The thing about comet prediction is that it's notoriously difficult and unreliable. So if you see a prediction saying such and such comet will be really bright, don't take it too seriously until it actually happens. And if you see a prediction that says, oh, this comet will be completely invisible, well, stay tuned. Maybe it's going to be the next great comet of the century.
Indeed. Okay, so there are some questions. So there's a little bit of a misconception in some of the questions that have come in the last few minutes. One of the questions is, did Yuguang say the CGM might be the explanation for dark matter? Would that explain the rotation curves of galaxies? I'm just going to jump in here a little bit. So there are two missing matter problems in the universe. One is dark matter, the thing that we've had to invoke, and we've known about this, there have been hints of this since almost 100 years ago, first identified by Fritz Zwicky with clusters of galaxies not being massive enough or being too massive relative to the amount of light that they had. So there was some sort of unseen mass that was present, or the hugely important work of Vera Rubin about 40, 50 years ago, looking at how quickly galaxies are rotating around, and that they're rotating so quickly that you can identify how much mass is interior to their orbits, to the outer parts of their disks. And if you count up all the stars and the gas that's there based on the luminous light that's coming from it, it's not nearly enough mass to be able to allow this thing to spin at the rate it is without just flying apart. So those pieces of evidence are what suggests that there's missing material, a substantial amount of missing material in a lot of galactic or larger scale objects throughout the universe. And we think that's why we invoke dark matter. And it's not because astronomers are uninventive or just grasping at straws. Yes, there are some really hard pieces of evidence that there really needs to be some sort of unseen mass there. The other problem, the problem that Yuguang was suggesting, is the missing baryonic mass. So there are additional pieces of evidence that suggest that even if you take into account and you invoke this dark matter, that there's missing matter from our galaxies, that there's more baryons. Baryons are gas and solids and all the stuff that we're used to, protons, electrons, neutrons, that sort of thing, that there's actually missing baryons as well in galaxies. Now, the circumgalactic medium can potentially fill that niche. It can fill the role of these missing baryons that exist within galaxies, but we can't invoke it to take up the amount of mass that we're required to have for dark matter. The dark matter mass is substantially larger than the missing baryonic mass. So I just wanted to clear up that misconception, because it's confusing.
Thanks.
Yeah. Do you have anything to add on that, Yuguang?
No.
Okay. Okay. More questions. Are there anything? Well, I'm grasping at straws looking at the questions that have come through. Do you guys have anything in particular that you want to ask or explain in the last 15 minutes or so? Is there anything you guys have been asked by friends or family members, or some excuse that you'd like to talk about something in particular? No? Okay. Well, the option's out there. Here's one. Can telescope design be improved? What do computer algorithms and simulations say about improving telescope design to improve capability? Yuguang, perhaps you can address this?
Sure. Yeah, I can talk a little bit on that, even though I don't work specifically on instrumentation, but I think I know something about it. So the thing is that I think the computer simulations in general has been applied to telescope designs all the time. So there are very powerful softwares, especially also commercial softwares, that people use to design lenses. So for example, you have a very powerful camera or a very powerful a telescope. These are all being designed on these sort of softwares. And these softwares can basically simulate everything from the light paths to the quantum physics effect of how your lens designs or telescope designs can affect the image quality. So these things are really being applied everywhere. The thing is that there are some hard limits on how powerful a telescope can be. There are very fundamental physical principles on how powerful a telescope can be. For example, one is the size of the telescope. And the size of the telescope can affect many things: your ability to collect enough light and your ability to resolve the astronomical objects that you can see. So these are the two very fundamental limits, and I don't think any additional improvements can be done with that. But of course, there are many ways that we can improve on certain types of telescopes. For example, there's a telescope called Vera Rubin telescope. It's designed to survey the sky very quickly, and also it's considered as the next generation after ZTF, the Zwicky Transient Factory. So this telescope has been specifically optimized to have a very large field of view. And also there are also all kinds of space telescopes, for example, JWST. It has the need that it needs to be fit into the payload of the rocket. So then you need this telescope to be small not like the ground-based telescope that you can waste a lot of volume with. So different telescopes have different needs, and these can certainly be optimized. Yeah.
Great.
I would like to point out that he was my TA for the instrumentation class, so he definitely knows a lot about instrumentation.
Thanks.
Awesome. Okay. Another question from our 8-year-old Penelope in the audience. She's had a number of good questions here. What happens when stars collide? So I can take this, but I don't want to hog all the questions if other people.
Yeah, you should take it. And I'm going to show that paper about the stellar merger of V1398, was it?
I don't know.
SCO?
Yeah, V1309 SCO, yes.
Well, I think the very short answer is that we don't really know.
Right. Well,
we haven't seen a lot of examples, but
we don't see a lot of examples, but we see what appear to be merger products in the form of blue stragglers. So if we get into the details of how stars form, there appears to be a maximum mass at which they appear to form. You can't form infinitely large stars because stars form, you have a big cloud of gas, and in that gas, there's some, it's made up of a number of different elements. And because gravity is an attractive force, so any two objects that have mass, say my water bottle and me, we each have mass, and so we're pulled towards each other. And as this becomes more massive, I get pulled towards it more. And that's why the Earth, which is quite massive, is pulling us towards it. But it also happens if you have a big cloud of gas that this parcel of gas and this parcel of gas and this parcel of gas are all pulling towards each other. So this cloud of gas is gravitationally collapsing down. And as it collapses, it turns into a runaway, and you get small chunks within that cloud that collapse onto themselves. So it's called fragmentation. This big cloud is collapsing. And when I say big, I mean on the order of 1,000,000 times the mass of the sun, something like that. Quite large, quite massive. And so you'll have this fragmentation, and each of these little subclouds that starts to collapse will eventually form a star. But we don't appear to see stars above a certain mass range. And yet, later on, in certain places in the universe, I don't want to get into a color magnitude diagram here, guys.
You can say we see things that don't look like they could possibly be stars.
Yeah, that's right. They look too massive and too bright for what would have been able to have survived to that point. Oftentimes, this is referred to, yeah. One of the examples, and I'm not going to get into why this is called this, but they're called blue stragglers. And so presumably, yeah, most of the universe is composed of void and empty space. And so the chances that two stars actually slam into each other and merge and collide is very, very small. But presumably it does happen, especially in dense environments like the centers of globular clusters, where it gets really, really, really dense and lots of stars orbiting around each other. And that's where you see an increased number of these blue straggler objects. But yeah, in terms of the details of how those actual mergers take place, Anna's exactly correct. We don't really see this happening live. And so it's hard to describe what's going on.
But there's a quite spectacular example of something that people have thought could be that. Michael, did you want to show the plot of 1309 SCO? Did you pull it up?
You're muted, Michael. You're still muted, Michael.
Hello?
Yeah, I can hear you now.
Okay, awesome. All right, so here, this paper is called V1309 SCORP, merger for contact binary. So this is like, I think the only example that we've actually observed of two stars merging. And it's very convincing evidence that that's what this actually was. So here's the plot that shows the brightness of this system with respect to time. So at the beginning, you can see the brightness varies a bit. Okay, so first of all, I should say the up means brighter and like down means less bright, right? So in the beginning, it's the brightness varies a bit, but then it starts going up and up and up, and at some point the brightness suddenly drops and then it shoots up. It shoots up by like 6 magnitudes, and 6 magnitudes is a factor of 200, 300. So this thing really became much brighter than it used to be. But like after a few months, it's dropped in brightness as suddenly as it began to rise. And right now it's pretty much back to the old brightness. So the other plot in here that's interesting is this one. So this system is a binary, which means it's 2 stars that are orbiting one another. And the period is how long they take to orbit one another. So this plot is a plot of the period as a function of time. So at the beginning, okay, it's like has this period, but then the period starts to go down and down and down. And at the very end, the period disappears. We cannot see the orbital period anymore. And that's a moment where the brightening happens. And after this event, after the brightness returns to normal, we no longer see this binary orbital period. So yeah, that's kind of how we know that this is a stellar merger.
There have been a number of other things similar to this that have been seen, but I think people just aren't 100% sure that it really was a merger and not just the explosion of one star.
Oh, okay. Yeah, I heard about one very interesting object that exploded in the 16th century. And apparently, like we have a historical light curve, like a very bad one, that looks something like this stellar merger. Let's see if I can bring it up. Okay, so it's not mentioned here. But yeah, try to look it up.
Are you talking about Eta Carinae? Like Eta Carinae, there are some claims that Eta Carinae is a stellar merger.
No, not on Eta Carinae. Let's see, lunar supernova, 16th century. Stellar merger.
All right, we're getting a little bit off here with.
Yeah, I can't find it now, but YouTube audience, find it yourself.
Okay. All right, we had a question. We've only got about 5 minutes left, but there was a question that someone wanted to get just before they went to bed. A 6-year-old wanted to get answered relative to Yuguang's talk, and that is, how is the CGM related to galactic star formation?
Yeah, that's a super good question. I can't believe it's asked by a 6-year-old. So first, so there are 2 ways. One is that when you have star formation, apparently when you need to form stars, you need some fuel and you need gas from other places. And apparently these gas comes from the universe, from the vast universe that falls onto the galaxy through the CGN. So this is the one way that star formation can be related to the CGN. The other way is that when these stars form, as I said, it will throw out a lot of stuff by stellar wind and also supernovae wind. So the amount of, for example, metals and also the other chemical elements that in the CGN can be correlated with the past star formation history, like how strong the star formations are and stuff like that. So either way, can be the precursors. So the gas in the CGN can be precursors of star formation. And also, we can see the relic of star formation in the CGN.
Excellent. There's one question that I sort of promised someone that I would answer. I feel like this is a plant because it's just too perfect. Do cosmic rays significantly contribute to the ionization of the circumgalactic medium? It's a pretty high level question.
Yeah.
but it's super relevant because one of our colleagues here at Caltech, a brilliant researcher by the name of Dr. Sucheng Ji, just wrote a paper all about this. And the long and short of it is that, so for those of you who don't know, cosmic rays are charged particles like protons or atomic nuclei that are traveling at very, very high speeds, near the speed of light. They get accelerated to these speeds by supernovae shocks. As stars explode, they have hot winds and that are usually charged at some level, and so they can accelerate these particles up to really, really high velocities. And because they're charged, they'll follow magnetic field lines and they'll kind of spin around them. And we're just now, in the last year or so, able to include the effects of cosmic rays in the simulations, like the simulations I showed earlier, the fire simulations. And when you incorporate these effects into our galaxy formation simulations, they provide an additional pressure source in the interiors of galaxies that's helping keep gas aloft, instead of the gas having to rely on its own thermal pressure. That is to say, collapsing under its own, collapsing for gravitational means and then puffing itself up by its own thermal pressure. So the cosmic rays don't directly ionize the CGM by slamming into it. It's more that their presence, because it's charged, influences the other charged particles in the CGM and provide additional pressure that keeps it aloft. And previous to this, when we didn't incorporate cosmic rays into our models, most of the circumgalactic medium was ionized through collisions, called collisional ionization. When you have two particles and they slam together, it kicks off an electron and it becomes ionized. But it looks like in the presence of cosmic rays, excuse me, there's still ionization that's out there, but it's primarily caused by photoionization. That is to say, really energetic photons, light rays coming along and hitting one of these particles and kicking off the electron that way. So I know that was a really detailed question and it's a really high level question, but I was too excited that this question was asked on Twitter yesterday. So I had to respond because this is like the cutting edge of what we're working on right now. Okay, do we have time for any other questions? Does anybody else want to address? What is your favorite exoplanet and why? Nicole, Mike, Jang, anybody else?
I definitely have a favorite.
I do too. Yeah. You can go first.
Okay, sure. So my favorite is the one that's behind me in my virtual background. Let me move out of the way so that you can see it. Oh. Okay, so this planet is called 55 Cancri E. It's a rocky planet. It's about 2 times the size of the Earth, 8 times the mass. But it looks nothing like the Earth. And one of the reasons it looks nothing like the Earth is that it's very, very close to a star. So a year on this planet will be 0.7 Earth days. That's how fast it orbits a star. Because it orbits so close to a star, its surface temperature is probably 2000 to 3000 Kelvin. So the surface is probably molten magma. And what else do we know about the planet? Well, maybe it has an atmosphere, maybe not. Maybe the atmosphere is hydrogen and helium. Maybe it's like heavier molecules like nitrogen or oxygen. We have seen evidence that this planet is variable in the infrared. And people have suggested that that may be due to volcanoes that are erupting. So you have a volcano erupt, it like spews a lot of dust into the atmosphere. It blocks the surface so that it appears dim. And then after a while, the dust clears and you can see the magma again. And that's why it becomes bright. We don't know. That's one of the explanations. So yeah, this planet is one that I'm studying for my thesis.
Yeah, my favorite planet is also one that I'm studying for my thesis, if you'll notice a trend here. So I think my favorite planet is probably P26b. So it's just a Neptune mass planet. It's a Neptune sort of mass. It's a gas giant planet. And you wouldn't expect very much to be special about it, except for the fact that it's one of the planets that breaks a trend that we see in the solar system. So I mentioned before that there's this trend between mass and sort of accretion of solids onto the gas giants in the solar system. So Jupiter, biggest planet, lowest atmospheric metallicity. Once again, it's just things that aren't hydrogen and helium, related to hydrogen and helium. And the smaller planets actually have much higher atmospheric metallicities. So in the solar system, they fall on this really lovely trend where you have this mass, the lower the mass, the higher the atmospheric metallicity. And HAT P26b was one of the planets that started people realizing that it's a lot more complicated with exoplanets. So it's a Neptune mass planet. You'd expect it to have a very metal-rich atmosphere. It does not. It has a very metal-poor atmosphere. So there's been that evidence from using the Hubble Space Telescope. I found very similar evidence that it's methane-rich using Spitzer Space Telescope. So I think that's probably why it's my favorite planet, is because it shows the diversity of planets, because we really don't fully understand the way these planets form and evolve. We can see things that we'd expect from the solar system to be true in exoplanetary systems, but the universe is complicated and it's never that simple. So I think that's probably why it's my favorite planet.
Excellent. Are there any other contributors who have a favorite planet? My favorite planet's the Earth. I really like it here.
Pop-out answer.
Yeah, I know.
Exoplanet. The question's exoplanet, Cameron.
Oh, exoplanet. Well, I don't know. Okay.
Earth. Pick an
Well,
Earth analog.
What's that?
Pick an Earth analog.
Yeah, we haven't detected any planet Earth analogs yet, have we?
Exactly. No, we haven't. And that's actually one of the things that actually annoys me a lot. You were talking about that before. You see a lot in pop science news, like the next Earth 2.0 has been found, and it's never true. It's always a planet that's similar in mass or similar, it's sort of similar in mass usually, similar in size to the Earth. But half the time those are super Earths, actually more often not, meaning that they're probably not remotely similar to the Earth. They could have hydrogen-rich atmospheres. Some of the planets that are claimed to be the Earth 2.0 are more similar to a gas giant than to a rocky planet. So that's just, I think, going back to what you were saying before, a thing to keep in mind whenever you read kind of pop science news. There really hasn't been a planet that's like the Earth that's been found. There just hasn't been.
Yeah,
But
well, Kepler was supposed to give us one or multiple, but then the instrument was like more noisy than we expected, and the stars vary more than we expected. So it ended up that instead of 3 years to find an Earth analog, we needed 8 years. But then the spacecraft broke after 3.5 years.
But there's also a point there that even if we find a planet that's exactly the same size as the Earth, that doesn't mean its atmosphere is the same. And that's kind of what I think of as an Earth 2.0, an Earth analog, is that it has to have a very similar atmosphere to the Earth. And that's the thing that we're missing. We don't have a good characterization of the atmospheres to that level really yet for planets that are that small. So I think that's kind of a big caveat for all of these things.
Yeah, like Earth's atmosphere is a product of life. So if you find an Earth atmosphere that's similar to ours, that would be really exciting.
And very hard to detect. So I would caution you to with that, but also suggest that people should go look at the literature also for astrobiology and show that there are certain things that can mimic biological life that are abiological. So there's always a ton of caveats that the astrobiology community has to kind of deal with and contend with when it comes to finding the next Earth analog or something like that. But it's definitely complicated.
The more we study, the more we realize there's a lot of things that can replicate biosignatures.
Yeah, absolutely. I think just the universe is complicated is pretty much what we learn as we learn more about the universe.
Indeed. All right, panelists, it is past 9 o'clock. Thank you very much for your participation. Thank you to our viewers. Our next event, we will be having a virtual astronomy on tap a week from Monday on April 20th, 4/20. So we encourage you, I'll post the stuff online. We encourage you to join us. We'll be doing it over YouTube Live. We will have more than just water bottles. We'll have beer, probably. Our speakers are talking about, it's a JPL scientist and a Caltech scientist talking about exoplanet atmospheres, I believe. So perfect based on our last conversation, and star formation in galaxies. So that'll be April 20th. Tune in, and thanks again to all of you guys, all of our speakers. Excellent job, guys, and we'll see you next time. Thanks, everybody.
All right, thanks, Cameron. Thanks, everyone, for joining us.